We all have been dealing with a lot since the pandemic has started. Indian healthcare workers are trying their best to control the situation. National Institute of Disaster Management encourages you to take the preventive measures against the coronavirus. Always wear a mask and sanitize your hands frequently. Also follow all the protocols of social distancing. Get yourself vaccinated from your nearest vaccination center. Until then, stay home and stay safe.
Okay, so a very good afternoon to all the attendees and the panelists for today. Today we are having the second day of our webinar, which is on comprehensive landslide risk management. So today, as a part of this session, we have three eminent speakers again. We start with Professor Srt Prakash. He is the head of the Geometeorological Risk Management Division and CBRN and Cyber Disaster Management Division, and he is the faculty in charge of 5 specialization centers: Center for Hill Area Development, Center for Early Warning and Communication, and Center for Coastal Disaster Risk Reduction and Resilience, Emergency Operations Center, Flood Monitoring Cell, as well coordinating the faculty of 8 central ministries, which includes Mines, Communication, Northeastern States, Petroleum and Natural Gas, Shipping, Labor and Employment, New and Renewable Source, and Parliamentary Affairs. So, sir, I welcome you to today's session, and I would request you to take over the session and give us your talk.
Sure, good afternoon to the distinguished experts who are participating in this program, our co-partners, faculty from IIT Mandi, and our delegates and participants. This afternoon, today our first program lecture is on the landslide resilient building construction. As you know, the incidences as well as the impacts of landslides seem to be rising despite all our best efforts. Although we have done a lot of landslide inventory and susceptibility zonation mappings and also some case studies, still there are so many instances which have been happening around us and causing losses of human lives, economy, environment, and infrastructure. And we have a campaign called Coalition for Disaster Resilient Infrastructure. We are talking about the resilience of infrastructure, including the buildings, against any kind of potential hazards, which also includes landslides, earthquake, flash floods, fires, and cyclones or tsunami, etc. Now, when we are talking about landslide risk management, this is a very specific program where we have focused on landslides specific hazard in the hilly terrains, and this hazard becomes more adverse when it strikes the habited areas. The highways or the buildings, they are engulfed along with them. The people, the occupants, or the people, passengers or the passers-by who are going through those areas or passing through those areas. So this brings our attention that we need to think about how the buildings in the hilly terrain should be constructed, where should they be located so that they remain safe from the threats of landslides, and what kind of construction techniques or materials may be required to construct such resilient buildings, along with the prevention and mitigation structures or mechanisms that need to be brought in place so that the safety of those buildings and its occupants can be ensured. Besides our monitoring and early warning systems in cases where the threats are imminent and impending and likely to result into heavy economic or human losses. So I'll just, before I take you, as you know, from NIDM, it is our humble duty and also responsibility to pass the message during this current COVID-19 pandemics to all those who are participating with us or interacting with us, the precautionary steps that need to be taken to break the chain of pandemics and also to control and manage the situation. So these recommendations which have been given by our Honorable Prime Minister, that wear your mask properly, maintain physical distance of minimum 2 meters, that is 6 feet, follow proper hand hygiene, and also get vaccinated. The 2 doses of vaccines must be taken up. So we are trying to follow our 4T method, that is tracing, tracking, treating, and also then Tikakaran. This is the 4th T, which has been added recently after the vaccine has come in January. So this is my humble request to all to kindly follow it. This is what we have also termed it as new normal or appropriate behavior during COVID-19. Now coming back to the landslides, as I told you, landslides have multiple effects in terms of its impacts. That is on the human lives, in terms of losses, and also the social impacts in terms of the programs, cultural activities which get affected. Then the physical infrastructure and structures or buildings. For example, I told you highways, bridges, buildings, all of them, or even projects, idle projects, they are likely to get affected by the occurrence of the landslides. And while we are facing the human, social, or physical damage and loss, it also results into huge economic losses, because one, that we have lost the land which gets engulfed along with the landslide. Other is whatever possessions we have over this land, which may include a building, bridge, or a highway, or even an agricultural crop or a forest, all will also be adversely affected. And besides this, the regular income of the people of those areas gets affected because of their disconnection from the rest of the areas, or the difficulties for access to these areas. The 4th one is environmental, which is ecosystem based approach. Means whatever resources, natural resources, maybe including water, land, biodiversities, or even the minerals which are present within those areas, they all can get affected. Now, reasons for these instabilities, if we broadly classify, depend on the terrain conditions, which may constitute the local geology, lithology, or soil mechanics, and also the morphology, drainage, and land use or land cover conditions. That includes geomorphology, hydrological conditions, and vegetation. I've shown you a three-dimensional diagram on this left-hand side, which is showing the different features of hill areas, geomorphic features, which can be witnessed or seen in any hilly terrain. Besides the terrain parameters which prevail all the time in that area, whether it is geology, morphology, hydrology, or land use, land cover, there are certain transient factors or external factors that may invade the stability of these slopes. Now, this may include the cloud burst, the precipitation. It may be long continuous precipitation, and also the short duration, high intensity rainfall. Or it can be high magnitude earthquakes, moderate to strong earthquakes that actually shakens the hill slopes and cause instabilities and result into earthquake-induced landslide or earthquake-triggered landslides, which may be the fresh landslides or reactivated landslides. Besides this, human beings have always been intervening with the nature, and they are either loading, unloading, or undercutting the slopes or changing the drainage conditions, and that's or doing sometimes blasting and vibrations. That also is leading to landslides. So these are some of those situations which we can witness. Now, if these are the situations that landslides are likely to happen and there are identified areas, then what should we do? What's the prescriptive method is to avoid? First, in any hazard, we say either avoid the hazard or avoid, keep yourself away from the hazard or keep hazard away from yourself. So avoidance is the best means. It's most economical and sometimes feasible, but other times it may not be, because you have a limited area of land and you have to go for some developments, and that is, you have to keep a balance between the development and the disasters, likely disasters. So first thing, as I have shown you in these photographs, if you look at the slopes which have already moved, have failed, actually we don't prescribe to construct buildings on them. Without proper stabilization and strengthening measures and protective measures, no building construction should take place in existing landslide areas. Further, you may have a building on the top of a slope which is unconsolidated, constituted by unconsolidated and loose materials, which can give way. For example, conglomeratic slopes or tops, which can easily infiltrate water and can come out or get eroded and cause landslides. And similarly, one should not allow construction at the top of the slopes. See, most oftenly we have a head-induced landslide or toe-induced landslides, because water mostly will go percolate down either from the head of the slope or will scour away the base of the slope, bottom of the slope, thereby destabilizing the slope and causing landslides. So any buildings located in these areas are likely to get affected by the occurrence of landslides. Further, one of the most common factors which has been considered as responsible for triggering landslide is hydrology of that area. That is the drainage fields. So pore water pressures can increase, and if it happens along with the vibrations, then the multiple effect of both the seismic vibration and pore pressures are likely to result into major landslides. While constructing buildings, we are modifying the slopes and the morphology or hydrology or land use and land cover of these areas. Now, while we're doing so, are we taking adequate cautions that to what extent these alterations should be done or should not disturb the stability of these slopes? So we have to actually analyze the slope through various parameters and identify the exact height, width, and length of the slopes which need to be managed for construction of the buildings. Because any overloading on any unconsolidated loose materials with adverse discontinuities can result into landslides, or presence of the drainage or saturated materials resulting to pore pressures and landslides. So there are possibilities, and then which may actually decrease the stability of these slopes. So two cases I've just shown to you here in this particular sketch diagram, where one is loading on the top because material is already not very strong. I told you it's unconsolidated loose weak material which is overlying on the top. And if it is loaded, it may move or get destabilized. Similarly, even the load uh, at other places, sometimes on the body of the landslides, can also destabilize. So there are different portions of landslides which need to be taken care. However, if you put this load at the toe of the landslide, it will act as a resisting force. It can increase the stability. So it will depend where you are making the alteration of the slope and what kind of loading, unloading, and drainage changes you are making on these slopes. I'm showing one of the good ways, better practice, I would say, in terms of putting load against the toe of a landslide in order to stabilize it, or in order to resist the movement of the mass, slope mass, by putting a weight against the movements. So people have created berms, and this weight of the berm actually is just close to the toe of the slope, ruptures surface of the slope, which actually prevents its outward and downward movements. So that will actually help in stabilize. So if we are finding, we are constructing a house on the lower side diagram on right hand side, I have shown you a building which is located on a slope. But now with that building, close to that building, they have created a berm so that the instability of this slope should not affect the building, and the slope should remain intact because of the opposition or resisting force uh, created by this berm. Then I told you loose and consolidated materials, weak materials, but there can be good strong rocks with the large number of discontinuities, structural or tectonic features. Now, in that case, there are likelihood of different type of landslides, which normally term as rocky landslides or the debris landslides generated by the rock debris. In this case, it may be a rock fall, topple, wedge slide, or a planar slide along a discontinuity plane or intersection of discontinuity planes, daylighting into the valley. So all these calculations are quite possible, and you can also determine the size of the block, which may move. If it is a rocky material dissected by different discontinuity planes which intersect each other, you can determine the size of the block also. And if water is seeping into these interfaces, it may be a foliation plane, bedding plane, joint plane, lineament, or a fold or a fault, or its axis like that. So which may actually provide a pathway for water to enter and to create pore water pressure. So those kind of things we can witness in the field. And if you find that, maybe the first thing, if you're constructing just below a rocky slope, we should trim that slope. We should actually stabilize those slopes so that the material which gets detached or displaced from those unstable rock slopes does not fall on your buildings or does not affect the occupants of those buildings by rockfall or topple. So you have to manage its slope, its geometry, and also its nature in terms of the material dissections and integration. Another simple feature I've shown to you on the down photograph also. So these are the ways we are trying to actually do scaling, trimming, and action to create a geometry which is more stabler than the existing geometry or the relief of those slopes or the morphology of those slopes. Now, if the slope height is too high, if slope height is more and gradient is steep, it's likely that material will come down because you know that stability of the slope will depend on the slope angles and also the cohesiveness and friction angle of those materials. Angle of repose will also determine the potential angle of slopes that can sustain and stay safe. So therefore, what we need to actually do that we maintain a relative height which actually stabilizes those slopes and does not destabilize. So we can measure the heights of the slopes, create benches so that stability of these slopes can be ensured. And now once you create benches with appropriate heights, now that need to be actually also maintained. So you can create some kind of structures. You can use bamboo walls, create a position, or you can do some kind of anchoring so that the material stays in place, because sometimes this material itself is also unstable and is likely to move. So this is what I've tried to show in these two diagrams, that in case you find the slopes are unstable due to the steep gradient or relatively high heights of the slopes, then we can modify those slopes geometrically, and that's quite economical, and then provide adequate protection structures or mitigation structures. Other ways to do this where instabilities have been observed around the buildings is construction of retaining walls. Now retaining walls actually have to have beep holes because water enters into the slopes from the uphill sides and need to be given away so that pore water pressures get reduced. And any such construction of retaining structures should also have an appropriate foundation at the toe, at the base. So if you have a space to construct appropriate foundations with a base slab and create a retaining structure by either on the breast as a breast wall or as a retaining wall, it will help stabilize that area and prevent the slope mass movements. And sometimes if you don't find adequate space and you feel that wall is not well integrated with the slope, then you can also use counterfort tie systems with that stem wall. Or these walls may not be just the cement concrete walls or boulder masonry walls or cut stone masonry walls or brick masonry walls, but you may also use some kind of reinforcements to bring flexibility into the walls so that it can actually have some kind of elasticity. And you can use steel bars, and steel bars if used, it will also help you actually reduce the sectional area of these walls. So these retaining structures, you can see on one side I've just shown you a sketch, on the other side I'm showing you a building with a retaining structure on its downhill side, so which is actually preventing the movements of the mass and also providing the stability for the structure against the impacts of the landslides. Now there are several means to provide stabilization in and around the building areas. Slopes little away from the building itself may also start sliding and retrogress upwards, and that retrogressive failure can lead to engulfment of a building. So for that reason, we have to actually not only take care of the uh, peripheries of the building, but also the surroundings of the building, which can also result into impacts on that particular building. So I'm showing you some of the features of retaining structures, I would say, or a crib wall, where these materials, you can use a steel material, or you can use a concrete material, or you can use wood material, or some other types of materials. and you make baskets and fill them with the debris material or the waste material so that they can act as a wall. And that bin wall should be well integrated with the slope and the ground so that it doesn't get easily dispersed or displaced. And just precast concrete blocks it is showing, and also sometimes even sandbags, they can also be utilized. And sandbags particularly, we have been using them into some of the areas where permanent physical construction is not possible, maybe due to certain constraints. For example, I remember in Goa, there is a Portuguese colony, which is a declared heritage area, and it is affected by landslides. And there, in order to actually maintain the stability of the slopes, these kind of sandbags have been placed to act as a retaining wall. On other cases, where the materials are strong and intact, you can use ground anchors, or good soil conditions, you can even also use soil nailing methods. But these are nailing techniques as not yet common in India, and it needs to be practiced more. And similarly, rock anchors with bolts or pretension anchors, these are possible mechanisms to prevent failure in the rock slopes. But there are three different types of materials you may come across in any slope in the hills. Basically, broadly, these are defined as the rock masses with discontinuities present within them or across them. They may be massive also. The second is debris. It's a mixture of soil and boulders or rock fragments. More than 80% is the aggregate rock masses or pieces which are found in the debris material. Then the UK may come across earth or soil, which has very small grain size, normally less than 4 millimeter, which can also get destabilized. Now, depending on the nature of the slope mass, we have to actually propose our protection measures in and around the buildings. For example, I am showing you at one place there is a wire mesh, because small stones they can come out. So you have to decide the size of the mesh that so that the stones cannot come out, and this mesh need to be integrated with the slope and the ground so that it does not allow the material to get dislodged or displaced. Similarly, there are biotechnical measures which are being opted for the protection of the slopes in and around the buildings. Now, concrete measures, they do not provide good aesthetics to this environment. So therefore, people are using some kind of biotechnical measures which includes jute nets, quires, mats, or also vetiver glasses or some kind of other plantations, which can help stabilization of the slope masses. So depending on the site where a building is located or constructed, and then the construction techniques and the likely type of risks, the protection mitigation measures are undertaken in and around the buildings. Plastic mesh has also been used in some of the places. So stability problems most often occur when house is built over soft soils. Particularly, let me tell you that if you're having a mix of permeable and impermeable masses or materials, that can be one of the reasons for landsliding. Or materials made of clay minerals, for example, the montmorillonite or bentonite, which swell and shrink very fast with the ingression of water into them. And this sinking and swelling results into sometimes development of the cracks, destabilization and displacement of the slope mass. So this kind of nature of the material underneath the building or around the building must also be properly examined, and one must get the geotechnical investigations done into those areas besides the local geological, geomorphological, hydrological and land use land cover conditions. Determination of these geotechnical properties will include the stiffness, compressibility, cohesive forces, and pore water pressures that are likely to affect the strength of these materials. Both the kind of tests, the in situ tests in the field or laboratory tests by taking the samples from the field to the laboratory is possible. Now, as I said, there are different types of soils. You may have sands, you may have gravel, or you may have loamy sands, you may have silt, you may have clay, or a mix of them. Now, when these materials somebody works upon for the purpose of construction, they react. They react to the loading, change in drainage condition, and also compaction or other processes being followed in those areas. I'm just showing you a picture where a compression leads to the upcoming of a soil mass, because now this mass which is unstable in one area, when it gets compressed, then the other areas they exerts those tries to release that compaction forces or the compaction pressure, and we have to actually compress or compact the whole area. Soil improvement techniques are many. One is static loading conditions. You just put up load at a particular site under pressure of that static pressure, the soils get condensified and compacted. But you can also use the dynamic compaction techniques or the rollers, which actually use the cyclic loading conditions, making it stronger over a period of time with multiple impacts of that load or the mass being done through a dynamic process. Then buildings, if you find that they are located on materials which has thick deposit of unconsolidated or loose or weak materials, and you may find a rocky mass below that layer of materials. Maybe it is say 2 meter, 3 meter, 5 meter. So where if it is like that, some kind and a big construction, a building construction is required, then you can also go for pile foundations. Now, pile foundations maybe you can have a precast pile, or you can go for in situ pile construction techniques. And these piles will actually take the foundations into the stable rock masses, and will then the building will not get easily affected because of the superficial unstable soil mass or the debris mass. Or sometimes people can also use some kind of chemical mixture or material, or sometimes physico-mechanic techniques, thermal techniques, or osmosis techniques. So there are different ways of making materials stronger or taking your foundation to the stronger materials so that the buildings remain safe. The other parameter, if you're using building, I remember one of the buildings which got affected. Most of these buildings, it may be a residential building or a commercial building, maybe a guest house or a hotel or some other market areas. Then lot of water gets released from such buildings, and this water actually percolates into the slopes and continuously 24/7, 365 days of the year, it is destabilizing the slope mass. So one has to take care of the drainage as well as the sewerage measures or drinking water supply into that building, so that leakages do not happen and destabilize the materials, or maybe you have the swimming pools, gutters, or even irrigation around the buildings. So all these where the water can actually become a cause for the landsliding need to be well taken care. Any water which passes close to these buildings should either go through a lined pipe or a lined canal or a lined system of channels to dispose the water in an appropriate place. So these are some of those suggestions which I have told you. But one of the important thing that you may have to take care is that because we are constructing on slopes, and they will have always some degree of instabilities or some kind of movements, displacements. In those cases, the material that we use for the pipelines or the channels, we should do that with some flexible materials so that it doesn't get easily ruptured. So that kind of design and material must be utilized. Control of water. Sudden, speedy, fast flow of water can lead to scouring and erosion or loss of toe or bottom of the hill slopes, causing landslides. So normally in our Indian standards and codes, we are prescribing construction of side canal, side drains along the roads, and also the disposal of this drain water through culverts into the main river system in an appropriate manner. So similarly, for the areas which are covered by the buildings, we should also have an appropriate drainage design and construction as well as maintenance so that the drainage does not affect the stability of these slopes. I've shown you different types of culverts or the pipes which have been utilized. There are so many types of pipes, but just for example, I've shown you a flexible pipe or a slab culvert or an arc culvert. So there can be many design depending on the geometry and the materials being used. And regularly, it is important if you are living in a building on a slope to check it for its any kind of signs or precursors of land slope failures. And these will be maybe in the form of development of the cracks within the ground, within the walls, or maybe no observation of gaps between the frames and the walls or the doors. So all these kind of things which we have been informing must be witnessed, and also if you are seeing them, then you should monitor them well. So you can see sometimes some kind of differential settlement, sometimes bulging, or sometimes maybe the development of the cracks within the building or around the building. So in the cases, you must use some flexible structures using the brickwork or concrete work or timber or steel frame or panel claddings so that the movements can be registered or opposed, and water which is actually blocked and creates the pore pressure may be appropriately released. And if it is the relief or the slope gradient which is making it unstable, that should also be modified and then adequately protected with some engineered retaining walls or biotechnical measures at an appropriate slope and with an appropriate height. Now there are in hills, some of the buildings, they are actually constructed on the original masses or slopes, ground mass, but there are buildings which are partially constructed on the hill slope mass and partially with some fill materials in order to increase the space or enhance the facilities. So now the integration of this fill material or slopes made with fill materials along with the original hill slope masses may not be very good. That may gap interface may also lead to some kind of surface of failures. So that should be properly integrated and reinforced so that the building does not fail. You may use a structural ring beam at the top of the doors or the windows or the walls to the columns so that they work as a unit, and this unity of the different element of the buildings will provide the structural integrity and also resistance against the landslide. Just showing you some of those buildings where this kind of integration mechanism have been followed. You can see the continuous ring beam over a house, or you can also see on the other photograph where connection between roof and wall has been shown there so that they can get well integrated, and also reinforcement within the walls, and also placement of sandbags. So these are some of the things which need to be done. Now, in any building construction, you are using different type of aggregates, which include the cement, sand, and aggregate mixtures, and there are different prescriptions for different type of environments under the codes, which I have just listed. That if it is mild environment, which means the concrete surface protected against weather or aggressive conditions except situated in the coastal area, you can use reinforced concrete with M20 ratio. That is 20 megapascal should be the strength of that uh, no material. Then you can use these similarly in other areas. As you go in the higher areas where the risks are higher, a higher strength of the material is required. So we prescribe M30, M35, and 40 depending on the situation into that particular area. Some important considerations. Now, first thing in any building construction is siting, where it is located, and the stability of the slopes where the plot is located or the ground is located for construction of the building. After you have ensured the stability of the ground or the slope for construction of the building, you have to actually look into the foundation of that building. Now that foundation should also get well integrated with the slope mass or the ground mass so that it doesn't move easily. So type of the foundation, material for the foundation, and the construction techniques also need to be well taken care. So I just suggested some of these foundation techniques which are being followed by our civil engineers. For example, for this uh, short story, small buildings like the residential buildings, maybe up to 3-4 stories, raft foundations is being used, and they are using this foundation particularly very good if you get across a rock mass, and if rock mass is fissured, and then we must go for grouting to strengthen that material or go for anchoring of that rock mass. And no trees that grow to a large size shall be planted within 8 meters of foundation of the buildings, because trees, their root will go deeper and will spread across the walls, and it will result into rupturing or cracking of those walls, and therefore their strengths may be lost and they can easily fail on any hill slopes. Just showing you some of the types of foundations that can be utilized on in the buildings on the hill slopes. That is raft foundation, strip foundation, pile foundation, and drilled piers. Sometimes when the building is too big and having load, and the slope mass is too unstable and weak, then we can also go for uh, pier drilling. And the traditional building materials which have been used include the earth, soil, wood, timber, bamboo, mat, corrugated iron sheets, stone bricks, concrete, asbestos sheets, lime, slates, etc. Whereas in today's world, people are using alternates. They are now using more concrete blocks, ash bricks, fly ash bricks, precast stones, concrete blocks, and stabilized soil blocks, etc. I tell you this example in Leh, when they were using the sun-baked bricks, they failed. The buildings collapsed when the flash floods happened in August 2009. Similarly, even the walling materials can also vary, both in the traditional and the alternate building materials being used. So I'll not go into more detail because I know there are other speakers also to talk. So I'll just skip the detailed part of it. You can learn more from our book that I have already told you has been actually prepared on construction of safer buildings on unstable hill slopes or hill slopes, so that or in the hilly terrains, that will help you guide, and different types of buildings. For example, earthen buildings, wooden buildings, or stone masonry buildings. They will have depending on the type of material and also the construction techniques, they will vary. And accordingly, we have to actually check, examine the impact of these buildings on the slope stability, and also take appropriate, timely protection and mitigation measures or preventive measures. Now, despite all our efforts, nature being mightier than the man, we may come across landslides in built environment. Now, landslides in built environment will also give us some early warning in terms of precursors or signs of failure. And these must be timely and observed so that the lives of the people are not lost. For example, I am showing you the crack in a building. Now, this crack may be in the ground, in the pavements, or it may be in the walls. So, one, if observes, should start looking for the possibilities of the landslides or cracks around the building or slumping or differential settlements. So all these things, I can show you one of the photographs where a landslide had been witnessed at the back of the building. Now this slide, if it continues and this rupture surface goes below the buildings, then building by itself can also be engulfed by the landslides. Besides the elements of the building, there are many service lines, utilities, for example, sewerage pipeline, drinking water pipeline, or some kind of irrigation pipelines or canals, which may also get leaked or ruptured and release water into these slope masses and result in landslides. I remember there was a landslide in Sikkim, close to that Sikkim Supreme juice factory, uh, when this leakage from the pipe actually led to destabilization of the slope mass and a major landslide that actually affected that factory also. So you can see these kind of signatures which are possible, and in a short comprehensive preview, we have kept actually a slope with unstable masses and a position likely to move, and a construction of building along with the highway and drainage. I'm showing you a poor practice where no adequate preventive mitigative measures or preparedness measures or monitoring measures has been undertaken. So this building along with the occupants is likely to get affected by the landslide, by the rock falls, which may happen at any time, maybe because of infiltrating water, heavy precipitation, or earthquake vibrations, or undercutting by the construction works, during the construction works, or also the drainage being released from the house into the slopes. So these are, and also barren slopes because of no vegetation and deforestation. So, and the slopes are very, very steep with very high heights. So these are the situations that one may have adverse situation. Now, what can be the better practice or the good hillsides practice, that take adequate appropriate siting or selection is first. One must see that you should select the least hazard, landslide hazard prone area or susceptible area, and then follow very good practices of construction, including stabilization of the ground and opting for appropriate foundation, and also the materials for construction of that building in a landslide resistant design manner. So with adequate land cover and drainage measures for the stability of the slopes. So these are some of the things which I just wanted to share. There are so many things one can share. Even for siting, there are guidelines. And in old times, people you don't use not to construct the buildings close to the foot of the slopes or the toe of the slopes, or just at the ridge of the slope. So they were very well knowing by virtue of their living experience. But with the passage of time, we have lost that no traditional wisdom and worth to recognize that, and hence we need to work on it and give appropriate solutions for landslide resistant buildings and infrastructure. So with that, I close this PPT, and if there are any questions, I would be happy to answer.
Sir, thank you very much, sir.
Yeah.
It was really wonderful to hear from you. And I mean, you have in fact connected the point to the next presentation, what we have, which is on the engineering approach to evolve the landslide mitigation measures. So this is given by Mr. Ashish Garpure. He comes from Genstru Solutions. So he's already here. So already we have a little of time we crossed in. So we will take probably the questions to the end, or if it is possible, sir. Sir, you are muted.
I'm Dr. Uday. Actually, I have some other meetings also.
Oh,
so
okay, sir. Okay,
you can pass on through email.
Sure, sir.
I will be there most likely on the last day also, because I'm partner to this program. And
sure,
I
sir.
know Ashish ji will be covering a lot of these prevention and mitigation techniques. He's very good field professional.
Yes,
so
sir.
I think participants are likely to receive a good rich knowledge about landslide risk reduction using physical or structural measures.
Right, sir.
Thank you. Then if you say, I'll just join.
Thank you very
later.
much, sir.
Okay?
Sure,
Thank you.
Sure,
Thank you all.
Thank you. Bye, sir.
Bye.
Thank you, Surya.
So can I now mostly the questions we are having the questions, we'll try to answer it probably to the end of the session, or definitely by tomorrow. So now let us move to the next interesting presentation, which we'll be having from Mr. Ashish Garpure. So yes, hi. So it's actually a pleasure to hear from industrial experts, especially from someone from Mr. Ashish Garpure, who we can see now. And he's a really good practitioner. If you remember in the yesterday's presentation by Dr. Bandari, he also mentioned very clearly that we are going to get a good information from the presentation from Mr. Garpure. So without taking much time, let us quickly. I will introduce the speaker before we give him the chance for presenting the slides. So Mr. Ashish Garpure is a licensed professional engineer. He is registered in the state of California and Maryland in USA, Engineering Council of India, and Mumbai Municipal Corporation, with diversified experiences in various civil engineering fields, and has been associated with number of prestigious projects in India and abroad. He is the recipient of Supreme Best Engineer Award in 2012. And he has contributed to many IRC codes, including the state-of-the-art design and construction of rockfall mitigation systems, Special Report 23 by IRC Highway Research Board. So I'm sure if you are mostly working on any mitigation related aspects, I'm sure you should be either in contact with him, or definitely you will be getting into contact with him. So quickly, I pass on the session to Mr. Ashish. Please take over from.
Yeah, sure.
Thank you.
Thank you very much for that introduction. And yeah, I thank Professor Surya also that he set the tone actually, that he was already talking about mitigation measures. I'll just set time. I still have 30 minutes to present, 20
Yes,
minutes,
please.
right?
That
Okay, I'll
should be
try
fine.
to wrap up as fast as I can. So
Thank
uh,
you.
I'll straight away go to share the presentation, right? And that way we can probably. Okay, hope you can see the presentation.
Yeah, we are able to see, but it is not in the presentation mode. Yes.
Okay, is it now?
Yes. Can you
So,
just move the slide just to check?
yeah, okay.
Yeah, perfect. Thank you. Please go ahead.
Okay. Right. So we'll be talking about engineering approach to evolve mitigation measures for slope stabilization. And I'm sure that you must have heard by now the causes, the phenomena, what is the landslide, what is the difference between landslide, rockfall, and so on. So my idea was to focus on that. We know that it's a issue, slope stabilization issue. Now, how to approach it in an engineering way? Uh, Typically, what happens is people think that an expert would come and then he will solve the problem. And I just want to go to show you to how the things are evolved, because there is a deep investigation needs are there, and only after which we'll come to know the phenomena and then can probably give the solution. So the way I have organized my presentation is just a brief preamble. So just to set the tone, that was what is slope stabilization, what is the spectrum and spread of it, what are the mitigation measures or mitigated. So very brief, uh, and I also want to point out what are the complex geological issues faced, and the importance of input data, and the team and the roles. I want to highlight again that it's the team which works and not an individual expert. And after that, we can go into what are the observations needed: surface observations, subsurface observations, mapping, what kind of analysis is needed, establishing causes, phenomena, failure mechanism, and then getting into mitigation. But even post mitigation, what kind of monitoring is needed. So I'm leaving out the mitigation. There is a whole new dimension to it, but I'm leaving out. I'm just focusing on approach of it. Okay. So slope stabilization spectrum: unstable slopes due to natural or anthropogenic activities. And you've seen all this photo living in Himalayas, Mandi people there. So definitely you must have heard about Kedarnath tragedy. That was a debris flow due to huge mud flow. Um, we have worked here as well. Then Konkan Railway's laterite soil and rock sliding down. Then rockfall even in East Coast, right? Granite rockfalls are there. They work for Bombay Pune Expressway, so Khandala Tunnel and Doshi Tunnel, what were the issues faced there. Another issue of beyond landslide, but which can be catastrophic and people don't realize it, is erosion. That erosion can be as heavy as you can see the bottom part of this slide, that there could be a big hole even an elephant can go in, and eventually this leads to caving in of slope. Right? So what type of mitigation measures? I'm just presenting a menu here that how to categorize stabilization measure, either geometrical corrections, or topographical corrections, drainage, very, very, very important point in, mitigating the landslides. Retaining structures, there are a whole lot of retaining structures you can consider. I'm just bundling it into one. Internal slope reinforcement, so anchors, nails, and such practices. And some special measures like cut and cover, portal extension, reinforced soil walls, etc. When we deal with landslide or slope stabilization with soil, when it's a rockfall mitigation, slightly different approach. We can go for protection measures, retention measures, or prevention measures. And again, there are subcategories as well in that. So mitigated slope, I'm just showing few of the mitigated slopes. So geometrical correction, reinforced soil structures, right? Anchoring, nailing with erosion control mat on the top, reinforced soil structure, portal protection works outside the tunnel, barriers, right? So these are just a glimpse of different solutions. What are the complex geological issues? Conglomerate material, which is soil and boulder mix, very hard to treat. You neither think it as a soil nor as a rock. So it's a very difficult material to treat. Extremely varying geology. So it's not that you look at one section and then you decide for the entire stretch. There could be varying geology in vertical and horizontal direction. So sometimes patchworks are needed rather than one single solution. Presence of treacherous soils, clay stones, right, shales, soluble rocks, so which can create sinkholes, huge subsurface flows leading to piping and boiling, and alternating strata between weak and strong material. So when you are at strong material, you can't visualize the weak material underneath, which can lead to a slide failure. Presence of underground aquifers and presence or absence of vegetation plants in specific cases. So even presence could be a problem in some cases, or in some cases, absence is a problem. So what we thought is that we actually are practicing it. It's not, of some theory book. We actually practice an approach to evolve mitigation measure, and this is how we have come up with a flowchart that a reconnaissance survey of preliminary cause of problem. Then you do topographical survey and geological mapping. Then geotechnical and geophysical investigation. With all these investigation, then you eventually establish what is the rock and soil properties. So if there is, structural geology and data interpretation, so after getting all the data, we have a stereonet plot, obviously for rockfall, not for soil or landslides. We prepare realistic shape slope model and analyze the slope first, just the raw slope, and then think, what could be the solution options. We run it by the local area, what is feasible, run it by the client, what is feasible, if needed, some reanalysis, and eventually we come up with a mitigation measure. And then comes really the important part is also drawing and detailing. So it's, thinking a single cross section and thinking that we have designed something is not enough. You need to close your solution end to end. So drawings and detailings are equally important. And of course, everyone is finally interested in costing. So BOQ specs and budgetary costing. Then you execute the project. At that point of time, you must monitor it during execution and post-execution with instrumentation and other monitoring methods. So this completes the whole cycle. So people think, as I said, that some expert will resolve. I'm just showing that if you have a geohazard solution to be evolved, then there's definitely a geotechnical engineer, could be a team leader. But along with that, if you have mitigation measures, sometimes it could be a suspension bridge or a bridge or a culvert, or so a structural engineer. We need to know the topography and key feature identification. So you need a surveyor, you need an engineering geologist for geological mapping, kinematic analysis, rock mass properties. You need a geophysicist for subsurface mapping and interpretation. And as if this is not good enough, you need to have other data as well. So you need to have knowledge about geomorphology, hydrology, environment, bioengineering and horticulture. Sometimes, vegetation itself is a treatment. Construction management practices, because the solution you are giving must be viable and constructible. So a dimension to that. seismology and earthquake engineering. So you need to know the triggers and how does it affect instrumentation and telecommunication. So what we observe, starting with observe, so you can see that we observe the patches, where are the wet areas, how the orientation is there, with, what kind of issue is there, like gully formation, surface erosion, water seeping out. So first visit to site actually sets the tone at what you want. So some visual observation, like you can see the trees around, and just by the movement of trees, you can make out, which way the topsoil is moving and what is happening. Look at the tree shapes. So it shows a very gradual creep must have been happening. The random pattern, both side tilting. So you are probably at the valley where, you are seeing the heaving part as well as sloughing part together. So then you can use topographic survey for landslide monitoring and observation. And the technology like LiDAR is in practice. I'm personally fan of even drone survey because you also get the visuals very clearly. But there are, so many methods for judging what is happening. So even instrumentations like extensometer and clinometer, do triangulations. I'm just listed out that what all possibilities are there. And this is the description that which method you can use for what. Continuous GPS method, INSAR, photogrammetric methods, LiDAR methods, geotechnical instrumentation method. So certain things are good, like, just to take a random thing, INSAR is a very good application via satellite imagery. But sometimes you will not get the data right away when you need it. So for early warning systems, you may have to take some time. Photogrammetric methods are very good, where you can visualize the things. LiDAR, where you get X, Y, Z data to very accurately, and this can be practiced in dim lights as well. And other traditional instrumentation, extensometer and clinometer, and so on. So this is a LiDAR scan. This is a project we did in Maharashtra, Saptashringi temples. So we had a LiDAR scan, so we get exact profile of the hill slope, which was very useful. But as I said, I'm more fan of drone photogrammetry survey. As you can see in this picture, this is a bird's eye view. The tunnel is here. This is a tunnel portal. And you can see all mixed types of rock, shales, sandstones, topsoil. And a good part of this, if you have a high resolution camera, you can zoom in and even feel the texture of the soil, how it is. And sometimes when you're standing there very close to this slope, you can't visualize all these things, which gets help from this drone survey and 3D imagery. So it's a very good tool. Another drone image. So when we went to this site and we were standing at this point where my arrow is, and we thought that the landslide is this, okay, a shallow one, until we got this drone image and we found out that much deeper penetration is there on the slope. So, these are the advantages of using the technology. Then you can also convert these imagery into traditional contour maps. You can, these are very useful to spot the drainage locations, either existing or where you can drain as a part of your mitigation measure plan. Malingaon, this tragedy, where around 200 people got killed, we had this complete 3D image. So when you stand again at the bottom part here, you can hardly see the entire slope. But with the drone, we could see right up to the ridge what is happening. It's all surface stripping which happened. Just by surface stripping, it actually consumed the whole village into it. Right. So other, how to identify things, and so use of drone survey and observation. So we also get to know the fractures, foliations, and details of surfaces. Then you can, depending on site conditions and observations, categorize the site slope based on height, based on inclination, based on type of geology. So you have roughly, you have started converging, what type of failure to expect. Now, categorization, whether it's a soil strata, rocky strata, mixed strata, right? And whether the erosion is present, surface erosion or subsurface erosion, what's happening and why is it happening? So these are gradually giving us, narrowing onto the solution. We always carry this kind of geological mapping sheet, field observation sheet, so that we can map and note whatever we feel at site. So all the time, this imagery cannot help. A visual observation is needed. So we note it down, including at the site itself, we try to see that what kind of solution we can think of, right? Subsurface investigation. So this was surface or a topographical survey. So we do now going to subsurface investigation. Electrical resistivity tomography is a very good method, typically to detect even the water layer and how the strata is. So this is one particular site, mile 9 in Sikkim, and where we, this now it is called NH10 actually. So there was this Nala, Rani Khola, and this was eating away the toe, and gradually the reflections were getting right up to the road here. And we did some ERT surveys there, right? And with all these, you can see the blue area, which is the low resistivity, expected water lines. And we connected, we ran all the red lines you can see were the ERT lines. And where we got those blue areas where the low resistivity, and we actually tried to connect that, we could see that there are several underwater, under surface water passages were there, and which were eroding away the subsoil. So we get to know the root cause of this subsidence. Similarly, another area, this is in Maharashtra. And here also we conducted ERT to get to know what is the surface and subsurface. Sometimes, you also come across surprises, as you can see the dark area here with, sudden high resistivity. And we were not sure what is there until we went into detail and found out that there is a buried rubble masonry. And you can see this when we exposed it. So it was giving us a very high resistance. So we could come to know there is a structure there. So even, underlying structures can be detected with some anticipation. Seismic refraction tomography. So you get the substrata profile in there. And again, you can, in a qualitative way, relate to the strata, that whether what kind of strata, whether material, sand, limestone. This is a wide range, so it only gives you qualitative assessment. You need to know the local geology to say for certainty what is which is expected. Now, if you go to Srt Profiles, the advantage of doing this subsurface profile is that once you do that, you can actually reduce your traditional investigation, which is boring and logging. Because suppose you get to this, then you can plan that, okay, I'm not going to do every, say, 100-meter a borehole or some random thinking. I can actually select where my borehole should be, where the variation in strata is anticipated. Maybe you can plan and reduce your number of boreholes. Where uniform strata is there, you can, reduce the number of boreholes there. So this is also one of the advantage. But of course, along with this geophysical testing, you must carry out the traditional geotechnical investigation, but because here it is where you get the real samples, where you can see, feel, touch, test, and then be sure of. So you do the field investigation, you do the lab investigation, and find out the properties of soil and rock. So now, after testing and all, you have all the data which is needed for you. you can now think of, okay, if it is say a rock surface or something, then you can know the RMR of it. You can convert it to more Coulomb method and get C5 also of the rock mass, right? So you can use Rock Lab as the software for converting. Then you can plot stereo net once you know the orientation of the rock joints. You can plot stereo nets. Just a general category, I'm just showing that if the dip, the slope and the dip angle of the bedding is in the same direction, with the dip angle of bedding slightly flatter than the slope, you anticipate a slide failure. Similarly, if the two joints are there dipping in the same direction as of the slope, you may expect a wedge failure. If the dip is on the other side of the slope, then you may anticipate toppling failure. And if it is highly jointed or a lot of discontinuities, then the behavior of rock is more like a soil. So you can even anticipate a scoop kind of failure. So these all are observation, interpretation, and after that you come to know the phenomena, because unless you know the phenomena, you don't know what to do, right? Then you are just going with standard practices. So this is what we conduct. So now we know what is happening, whether it's flow or toppling or slump or slide or creep or fall. And then we know that what kind of solution might work, right? So analysis and design is then taken care. You have all the surface data, you have the geotechnical data, and then you can probably model it, analytical model with the right kind of strata, either limit state method or through FEM. Typically, we use FEM where deformation gets critical and you want to model that. So LEM or FEM analysis, you come to know the factor of safeties are low. Now you want some kind of intervention. So say this is a rocky area, Purnagiri temple, and we modeled the deformation as well. So because those were causing trouble, the temple was seeing cracks. So we can do this kind of modeling. Now coming to slope instrumentation and monitoring for early warning system. So what data what can trigger a slide is a threshold rainfall, flooding event, seismic event, slope geometry alteration, forest fire, construction activity, blasting, right? These are the typical trigger which will start a landslide. And what we can monitor, right, directly on slope: ground movement, ground acceleration, water table, pore water pressure. So then you instrument your entire slope so you know what is happening there and attend to it. So there are also this radars which can give even the movement of any particular point you have noted and put. And you see the acceleration. Whenever the acceleration is higher, then you know that the slide may occur. So there is a elaborate arrangement where you can have multiple data consolidated into a single receiver system, and it can be actually transferred to your mobile or laptop, and then you can see what is happening, and you are ready for early warning. You can even map with continuous data. You can even map a digital terrain model or digital elevation model, so that before the movement and after the movement and how much movement is there in a 3D way. So you know what is happening, where it is severe, where it is as a reflection of and you can even monitor these kind of thing, displacement versus time. So there are various type of failure which happen. You can see that here the displacement versus time was very gradual, and suddenly at one point of time the landslide triggered. Sometimes it is a curve, so you have exponential variation, and then definitely this is very typical when the failure is pointed. Sometimes, various curves like movement and consolidation, then movement and consolidation and some point of time. So if you leave your judgment, when the consolidation has happened, there is no more displacement, and you stop monitoring it, you never know when this next series is picking up, and it may trigger failure. So keep monitoring and avoiding. Water pressure monitoring, so you know then pore water pressure is rising, your safety factor is coming down, so you have to establish a threshold and you don't want to cross that. Before that, you want to take action to take out the water from the metrics. So coming to summary, that slope stability issues need careful data collection. Drone survey and geophysical tests augment and improve observational and geotechnical parameter assessment. Various monitoring tools like geodetic monitoring, satellite or drone monitoring, other imagery systems, settlement gauges, piezometers, rain gauges, ground acceleration monitoring tool, etc., have enhanced precision and eased the data collection. Early warning systems and mitigation measures designed on reliable data would enhance the performance, optimize the cost, and reduce the risk of hazards significantly. So thank you very much. I try to, I know I have rushed it through, but I'll be available at this number and this email ID in case anything is needed from my side. So that was the focus of today's presentation. Any questions? Welcome. Or if the time is exceeded, then probably I can take it on email or mobile phone. Thank you.
Sure. Thank you very much, Mr. Ashish.
Welcome, sir.
Yeah, sorry, thank you. So I have few quick questions.
Sure.
Actually, a few things I thought it's slightly outside my expertise. So I just wanted to find out from your side directly. So I have a question from NDRF. So there is a question which says that is there any way to ascertain the possibility of another landslide at the current landslide site where work is going on or the rescue operations are going on?
So by monitoring only. So yes, the chances are there. And in fact, if you saw the other slide, that even if some slide has happened, there is a possibility of a follow-up slide as well.
Okay.
Right. And yes, as an NDRF, you should be, especially careful about this because you don't want to put your people in the jeopardy. It is possible. And how to monitor, again, probably first thing to do, because it's a very rapid thing, I don't think you'll be able to instrument it fast. So maybe surface monitoring is that can be established very quickly. So, a moving camera at some distance, and, you put some patches, reflectors, and keep on monitoring them and keep on, the data can be transferred to your laptop, so somebody can keep on seeing it. Whenever velocity or the movement is slight problem, but more problem is acceleration. The moment you see that the movements are accelerating, then that is the time where you have to stop and alarm yourself.
Okay, that's good to find.
Surface monitoring will be better for you.
Yeah, thank you. So there is one more quick question. So what are the best strategies for mitigation of sinkholes?
The very unfortunate part is that sinkhole, unless the failure occurs, people are not noticing. Right. So very important is, even if there is a possibility, say a limestone, those kind of formations are there where sinkholes are there. Probably subsurface monitoring continuously through this ERT and SRT, even with a gap, right? Not necessarily continuous, but you at least should know whether void spaces are getting formed. And so that is to avoid. And if it is getting formed, then one way to establish or to mitigate it is that if you see the voids are coming, there are methods like very high strength geogrid can bridge the gaps. You still need to excavate, fill back whatever has eroded away, and you put some high strength geogrid across, or bridge where the void is there, and then refill it back and build your platforms on top of it. But the key thing is to avoid to keep on judging where the voids are getting created due to subsurface flow. Another way of monitoring is whenever you are seeing that somewhere the water is exiting with a certain gradient, and if colored or some other soil is coming, that the sinkholes are getting created because soil particle migration. So not necessarily stone alone, but even things like phyllites and all this foliated surfaces rocks. The very continuous soil particle migration keeps happening. Sikkim Mile 9 was the case that it didn't cause a hole because it was slightly deeper, but soil particles were migrating. The matrix was getting more honeycombed, and it was collapsing under the load. So it kept happening for a couple of times, and monitoring will definitely help. But yes, bridging is also possible, and reducing the water pressure through giving a good outlet, so it is not going in a particular direction and taking away the soil particles is essential.
Right. Okay. Thank you. Though there are a few more questions, but I think there actually the follow-up sessions also can be mostly answering there most of the part. So I will probably stop the question answer session here as well. So again,
Yeah.
thank you very much. Thank you very much for your very, should I say, there are some missing points which I wanted to look for when I'm looking into field investigation. I think your topic has really covered that particular missing points, which probably the other faculty were probably leaving it, and especially yesterday there was the same point which was raised by Dr. Bhandari when he told that when he saw your schedule and he saw that you are doing it, so he wantedly left a small topic in on-site investigation and how to approach the problems,
Right.
saying that this should be covered by you, and rightly you have did the same thing. So
Right.
thank you again very much for your time as well as your presentation. So from all the participants, I will again thank you very much for this, and I look forward to again meet you or talk to you sometime definitely.
Sure. Pleasure was all mine. Thanks.
Thank you. Thank you very much. Okay. So now we'll move to the last session for the day. So again, with the continuation of yesterday's talk by Dr. Bhandari sir. So he told very clearly that this particular talk will be of interest to all of us, because when we talk about landslides, we have been hearing into a prospect of only geotechnical engineers. So now let us invite the next speaker for us. He's Dr. Srt Srt Pradhan. He is a faculty associate professor in IIT Roorkee, and he is mostly towards the earth science department. So he will be giving us an idea about the engineering geology aspects, engineering geological aspects of landslides. So to quickly introduce the speaker, we already have here. Dr. Pradhan is a dynamic young researcher in the field of engineering geology and into reservoir geomechanics, who currently works as an associate professor in IIT Roorkee. So his works include geological and geotechnical investigations of rock mechanics and reservoir geomechanics. So Professor Pradhan is leading the geotechnical engineering laboratory at Science Department, which focuses on the soil and rock mechanical behavior of earth materials. He has almost like 4.5 years of industrial experience in ONGC before he joined as a faculty at IIT Roorkee, where he has associated with many projects of national importance. So with these few words, I would like to welcome Dr. Srt Pradhan. Yeah, he's already here with us. So we are just assigning you the presenter. I think you can start sharing your screen.
Yeah, good afternoon all. Thanks for a nice introduction. Yeah, is my PPT visible?
Yeah, it is. Yeah, it is loaded. Yeah, can you please change to make sure?
Hello.
Yeah, can you just change the slide once so that we are sure that things are working fine? Yeah, perfect. So, sure.
Okay.
I hand over the session to you. Thank you very much.
Thank you, Professor Uday. I hope this will be a very nice interaction with you all. I'll be talking about this engineering geological aspect of landslides. What happened where you are in field, there should be a communication which should be understood by your geologist and civil engineer, right? So I have put a few slides which may be a recap of your earlier lectures, and there are few things which I want to tell that, okay, on the basis of field investigation or the basic geological knowledge, how you can identify and address these landslide issues, right? And we know that the landslides are in mountainous region, and there are many types of landslides depending upon the material, okay, whether it is rock or soil or debris, okay, and the nature of movement, whether this is translational, rotational, like this, okay. So landslide is nothing but your rock or earth material that will move down the slope, right? And it happens in any slopey ground, okay. So what happens if you see why landslide is important and how we will address this? You can see, if you see the cost to benefit analysis of different natural hazards, you can see that the landslides cost to benefit ratio is high, right? That means if you prevent it, then we can save more, right? And we know that the ground conditions are really unpredictable, and as a engineering geologist, you should address this uncertainty, right? So that if you address this uncertainty, then that can be easily incorporated in your model for slope stability analysis, okay? So the ground risk generally that we can categorize into technical, contextual, and managerial, right? So the technical risk that involves encountering the unknown geological conditions, and you have incorrect design criteria. So we will be talking about these geological conditions, right? So what happens in any project you take, whether it is landslide, whether we are doing any tunneling or we are doing any dam site investigation, right? Initially, the uncertainty level is more and your knowledge is less, quality knowledge is less. And once you go from feasibility to the construction stage, then the uncertainty that decreases, okay? And your quality of knowledge increases, right? And once this decreases, then you are confident about your project, right? So we'll see about this unknown geological conditions, right? Okay. So I have divided these geological conditions into two types. One is micro scale and another is macro scale, right? In micro scale, you have geological material, and in macro scale, you have geology mass. Okay. So micro scale, what happens? You go to the mineral level, okay? Because we know that rock is made of minerals, and we will study the minerals level. Once that mineral constitute the rock, and that go to your mass level, mass fabric, you can say, okay? So the landslide is a process of mass wasting. It happens everywhere whenever this shear force is more than your resistive force, right? Or your shear stress is more than your resistive stress. So you need to characterize what is the what that contributes to this shear forces, right? What contributes to the resistive forces. Once you are able to characterize this, then you can easily analyze the landslides, okay? So if you have higher slope, suppose you have a slope and you have higher slope, the higher slope has more shear forces, the shear component is more, okay? Then this one, so there is chances of slope instability, okay? And the friction that resists your block, right? So what are the controls that affects this landslide? Okay, one that is driving force, and one that controls your resistance. So the driving force that is characterized by this material characteristic, what is the type of material, okay? What is the nature of the material, what is the strength of the material, what is the slope angle, okay? And the controls and resistance is the friction, because it's an interplay between your cohesion and friction, okay? So what are the factors that contribute to the friction? What are the factors that contribute to the cohesion? What are the factors that reduces your friction? What are the factors that reduces your effective stress, right? So that we should know. So we can divide the causative factor as natural and anthropogenic. Okay, in natural you have inherent property which is related to geology, means the rock or soil itself, and the external factor which may be due to seismicity and rainfall. And you have anthropogenic factors that we are doing while you are widening any road, you are doing any deforestation, you are doing any, you are not utilizing the land properly, right? You are doing ill-planned construction, that also lead to slope instability. So out of this inherent property, you can see how this lithology means the nature of the rock. The structure means what are the discontinuities present, okay? Whether there is faults, joints, fold, all those things. Then the slope itself, then the relative relief, land cover, then the hydrogeological condition. These all are inherent property that is specific to your earth material, right? And these external factors, these are triggering factors. It triggers the landslides, right? So let's go to this mineral scale, right? We have intact rock and we have rock mass. Intact rock means that is devoid of any fractures. Okay, you take a small piece of rock and you test it, you see what is the mineral composition, what is the density, what is the porosity, permeability, all these are related to your intact rock. Okay, the mineral composition that is related to geological origin, whether this is sedimentary rock, igneous rock, and metamorphic rock. And I will tell you how this can be distinguished. I have made this slide in terms of what I will say towards it can be applied towards the civil engineering people. It will be helpful for civil engineering people, right? Then you have geological history. What are the tectonic stresses there? What is the environment? What is the hydrogeological conditions and the weathering processes, right? Because you can see all these things, this from the origin to history to this weathering process, this affects the various strength parameter of the rock and soil, right? So we have mineral composition. From mineral, when we are talking about rock mass, that transforms into lithology. Lithology means your rock types. Okay. Okay. Then you have this fabric in intact rock, like porosity, permeability, alterability. When you are talking about a rock mass, that is your discontinuity, joints, faults, right? Then we'll see what is the state of stress, right? That we need to evaluate. Then hydrogeology is also important thing that need to be evaluated, because this water pressure, that is important. You know that this is the main culprit. Okay, if there will be rain, then it triggers landslides. Then we'll see if there is a slope sections, then there are different weathering zones starting from top to bottom. At the bottom you may get fresh rock, in the middle there is a mix, at the top you may get soil and debris. Okay, so these all individual layers should be taken care of, right? So as I told you that there should be reliable communication between geotechnologists, right? So this will help you. So what happens whenever you are doing any landslide investigation and you are seeing any rock, right? So go for the detailing. Okay, full description is very important. What is the full description? Suppose you are seeing the color. Suppose there is a slope and you say, okay, this is sandstone. But if you see, okay, this is a red sandstone, or you mentioned the color, right? Suppose I will say, okay, this sandstone you are saying that it's fine sand, you write fine sand, right? So these details, it will be helpful in encountering any uncertainty. Sometimes what happens, we miss the detailing, right? And suppose you have a fine sand, you have coarse sand, the property will be different. Only putting sand is not justified. So this, if you put this detail, then our project will be successful and our quality knowledge will increase. Okay. So what is the property of the measurement we need to do? We know to do this size and shape analysis of grains, then the density of grain, how they are packing, okay, then the nature and strength of bond between the grains, okay, and how they are distributed, whether this grain are randomly distributed, they are layered or oriented, right? suppose you have taken a rock piece and you have seen the grains are randomly distributed. In another case, you have seen the grains are layered or oriented in a particular orientation. If that is oriented in a particular orientation, that will give you a sliding surfaces, right? So that we should mention. As I told earlier, that okay, whenever we are doing any, suppose you are doing any soil or any sediments classification, we'll put silty sand. Means okay, this sand is, there are silt in this sand proportion is more. Suppose sandy clay is more, sand is less. So we need to put this. If you see, okay, there is an entire spectrum of your grain size. Okay, this grain size is given, then you can say, okay, this is silty, sandy, gravel. So from this, you can easily assess, or you will get a idea about the shear strength parameters, right? So we'll see how we can, on the field, how we can categorize this rock, right? So suppose you have in the field, and we'll see that okay, there are materials and you are applying this, you are squeezing it by your hand easily, then you can describe it very short. Okay, if this is not scratched by your thumbnail, then you can call it hard rock, right? So this field definition is given. Okay, if you see this field definition, you can say okay, that means this description means you can say okay, this is a very steep clay, this is indented by thumbnail, and I expect this shear strength around I will say 150 or 200, right? Okay, similarly, if you go to the rock, right, if you can easily crumbles in hand, that means this is very extremely weak rock, and its compressive strength will be very less. Okay, if there is thin slabs breaks easily under your hand pressure, then this will be very weak. Then you can put okay, the compressive strength is around 1 to 5 MPa. Similarly, all this field definition is given, which can be correlated with your strength, right? So why I have put this one, because this will be very much helpful while you are doing very preliminary study, which will give you a I will say qualitative idea, and that may translate into some kind of quantification, right? That will be helpful in studying the earth material. Okay. Then many times I came across how do you identify a rock into different types, right? Whether it is sedimentary, metamorphic, igneous, right? Then again in sedimentary rock we categorize into fine, medium, and coarse depending upon the grain size, right? So if you have a sheet like this, suppose those who are from geology background, they know this, but those who are from civil engineering background, it will be very easier for them to identify which type of rock is this, right? Okay. So if you have grains, and in between grains there is cementing materials, like you are making any concrete, you have chips, then you have cement, right? So similarly in rock also we will get this type of things. So that becomes a sedimentary rock, means the grain are bounded by sediments, cements, right? Then you have metamorphic and igneous rock. Metamorphic rock is generally foliated. There is layering of minerals that is visible, right? And there are igneous rock, which is crystalline, and the minerals are randomly oriented. Okay, so few of them are seen by your naked eye. Okay, and few are with help of lens. If you have medium grained minerals, and some are needed your high power microscope, right? So on the basis of this, you can categorize, okay, I have identified the rock types on the field. This is, suppose I will say sedimentary. Then I will see which type of rock is this, whether this is a sandstone or this is a calcite, right? So once that is established, then we go for this grain size distribution. Okay, if you are getting a sedimentary rock, okay, and the size of the grain is between 0.002 mm to 0.6 mm, means fine grain, right? then we call that as shale or mudstone, right? And this is known as argillaceous rock, right? Fine sediments. Okay. If you have medium size, like the sandstones, then those are known as arenaceous rock, right? And if you have conglomerated breccia, which is the grain size or grain size diameter is more than 2 mm, that can be categorized into conglomerate and breccia, right? So this is how you can identify the rock types there, right? You can identify the minerals, you can identify the rock types. Okay. This is what I told you. Okay. Then after this mineralogy, we'll go to the see what is the influence of lithology. Okay. Lithology means with respect to types, is physical and chemical characteristic of the mineral that is contributing to the rock, right? And you see, no rock is stronger than your mineral. Okay, always mineral is stronger. Then in case of rock, intact rock, I will say, if you take a small piece of rock, that will be less stronger than mineral. If you make it to a field scale, rock mass, then it will be, again, the strength will be less, right? Because once we are going from mineral to rock scale, intact rock scale, and intact rock to field scale, then what happens? You are incorporating many factors, right? There are natural factors that will be incorporated, and that reduces your strength parameters, right? So you can see, if you take this one very small fragment of rock that may be intact, which is devoid of any factors. As we are going to investigate more and more and taking this larger area into picture, then there will be more and more factors will be there. So this slope, suppose if I will take a small piece of rock from this and try to evaluate the entire slope, this may lead to erroneous results, right? But because the joints are present, and here you can see these joints that will be contributing to the failure of the slopes, right? So that should be included. You can see that Dr. Ashish also told about this, that if you have a slope alternating with your hard rock, soft rock, right? Then you need to identify. You can see here this rock seems to be soft and this is hard. So with time this will get eroded, and you can see there are many discontinuity present over here. And what will happen with time, with weathering, this portion they will fall, right? So we'll get a rock fall here, right? So this needs to be addressed, okay? Which I have to see the entire slope. I have to look at what are the lithology, what is the lithological contrast, and that I need to evaluate, right? And this is what I told earlier, though no rock can be stronger than the minerals of which it is composed. Okay, similarly, rock mass is not stronger than your intact rock. Okay, and while you are identifying your minerals or rock, right, that becomes very important, because if you are finding any rock which is calcite or gypsum, then you can say, okay, this is calcite and gypsum. If there will be any interaction with water, then it may cause serious problems, right? It may cause your landslide, it may cause sinkholes, right? So this need to be established in the field, right? You should identify the rock, and we can see, okay, what may happen, because if you analyze this properly, then you can foresee if there will be any hazards that are coming, right? Suppose you have rock salt somewhere, right? So what happened? The salt, they generally flow, right? They are plastic, so there will be creeping movement, right? So all these type of rock needs to be identified. Okay. Suppose you got rock, and in rock we are finding weak layers. We are finding layers or foliation that we know. Okay, if you are finding any foliation or any layer, and that is coming towards the slope, dipping towards the slope, then there is chances of instability, right? If you see the general strength of the common rock types, okay, we have igneous rock, like suppose granite, basalt, these are igneous rocks, right? So they are stronger, okay, Metamorphic rock, there are metamorphic rock which are very weak because this has foliation plane, or there is layering in this rock. Once there is layering in this rock, then it is susceptible to sliding. Okay. Then you have sedimentary rock, and in case of sedimentary rock, the rock strength varies a lot, right? If you have igneous rock, it's okay. The rock itself is strong, but if there is discontinuity in the igneous rock, then that may lead to instability. Okay, so we can categorize the rock on the basis of strength, from extremely strong to very strong, strong, moderately weak, and very weak, right? We can see how this density, as I told you, the density of the material that influence your compressive strength. Once you take a rock, and if it is closely packing, then the compressive strength of this material will increase. So whenever you are seeing, suppose you are seeing a basaltic section, and you find, okay, a few meters of the basalt section is having pores, vesicles, right? Then you can say, okay, these pore may create some problem, right? Okay, suppose you have sandstone. In one case, the sandstone porosity is more. In another case, the sandstone, the porosity is less. Then the having higher porosity, that may lead to less strength. Okay, and the weathering also influences these rock parameters or rock strength parameters. So whenever we are going to any slope sections, you may find that, okay, at the top you have your soil, okay, then you have your mixed soil and rock fragments, then you have your trace rock, right? So the weathering can be seen on field, and the evidences are like discoloration. Okay, discoloration of the earth material, then there will be increase in filling materials, right? Suppose in joints, there will be some infillings will be there. There will be decomposition of the material, right? So from this, you can categorize, okay, the different types of weathering grade. Okay, it starts from, there are 6 grades. If you have a rock, there is no visible sign of any weathering, we will call it trace rock. Okay, if there is discoloration, then you can say it is slightly weathered rock. And if half of the material rock is decomposed, then we will moderately weathered. Similarly, you can get, okay, if completely material is, there is no rock and it is converted to soil, then you will call it residual soil. So we can put this degree of weathering. Okay. So these are mineral stability. These are the minerals which are stable at the bottom. The quartz, muscovite, these are stable minerals. And these olivine, feldspar, pyroxene, amphibole, these minerals at the top, they react with the environment, and they alter easily, right? But you can see, if you have muscovite or mica, it is a foliated mineral, right? So then what happens? There will be foliation plane, and it may lead to your slides. So what happens if there is weathering? Then what happens? You can see, suppose you have a trace rock, and you find the RQD, suppose I will say 100%, there is no joints. Okay, and if it is slightly weathered, so instead of taking that 200%, you take the RQD factor. Okay, I should reduce the RQD to in between 0.8 to 0.9. Okay, similarly, once you establish the weathering rate, degree of weathering, then you can take this RQD factor and reduce your, okay, what should be the RQD, because this will be very much helpful while you are calculating your rock mass rating, or you are doing your slope mass rating. Okay, because suppose you are not seeing any visible joints, suppose you are doing any field visits, and you are conducting your RQD from a joint analysis, then you can say, okay, it's slightly weathered, then I will take, okay, I should reduce the RQD factor. So that need to be taken care. Okay, then influence of mineralogy, as you can see here. Okay, wherever you have your clay minerals present, its strength parameter decreases. If the clay minerals is make right, then it reduces significantly to your shear strength behavior. Okay, so if you have kaolinite, then it has the effect, but it is less affected, or it contributes less toward your shear strength, decrease in shear strength. You have spectrite, it contributes more towards your decrease in shear strength, because these clay minerals, they can absorb water, they have they alter their shear strength parameter. If you have quartz, then you will get okay, this is good, and the shear strength parameter will be more. Okay, so whenever we are doing any analysis, if you ascertain okay what are the minerals, clay minerals, then we can say whether there will be swelling and what will be the effect on this. I have seen in Eastern Ghat there is small smectites are there, and they are contributing to this failure of the slopes, right? Then you can see how this mineralogical composition alter the rock strength, right? Suppose you have kaolinite as a clay mineral, then you have feldspar and quartz. Generally, in sandstone, you get quartz and feldspar. Okay, so what happens if kaolinite percentage is increasing in any rock, then the strength will decrease. Okay, if you have more quartz content, if you have more quartz content, suppose you have two sandstone, in one case you have more quartz, then your compressive strength will be more. And similarly, if your feldspar is more, then it also reduces your shear strength. Okay. Similarly, the porosity, as I told you earlier, that suppose in case of basalt you got more porosity as compared to the other one, then you expect okay the strength to be less, right? So what I told you, that all these are field-based observation, and you can incorporate this in your preparation of DPR, right? Suppose you see here you have an impermeable argillaceous rock. Argillaceous means you have very fine sedimentary rock like mudstone and shale, right? And above this you have rock. So what will happen if this will be interacting with your water? Then what will it cannot sustain the support, right? Then there will be sliding. Okay, the rock becomes soft, and you can get this spread type of sliding, right? This already we have discussed. Okay, then role of geological structure on rock mass behavior. When I am talking about geological structure, means it's discontinuity, bedding planes, a joint. Okay, whether it is, suppose you have that in Himalaya it's formed because of this Indian plate goes inside the Erosion plate, and there are many faults, right? So is this slope is near that fault zone? Okay, if that is near the fault zones, there will be many joints and fractures, and this is the culprit for this landslides, right? So that we need to know. And you can categorize this type of discontinuity into different type. One is integral discontinuity, another is mechanical discontinuity. Okay. So in field, you can see many slopes. If you go from Rishikesh to I think Kodiala, then you can get many slopes like this, right? There are many fractures. They are intersecting with each other, and you get this type of blocks. You see this block. You can imagine if there will be slight disturbance, then what will happen? This will fall, right? This will fall. You can see here there is a fracture, and the fracture is growing. If there will be buildup in any water pressure, or it will detach from the slope face, then there will be a rock fall, right? I told you, okay, this getting this fault and fold. Suppose you have a folding of rock, right? Once you are getting any folding of rock, so once you are moving away from this hinge, means where your curvature is more. Here the material is crushed. You will find this joint very intense jointing here. I mean, this joint spacing is very less, and as you move away from this one, your joint spacing will increase, right? So if you are finding a slope and taking okay, the joint spacing is varying, you can categorize okay, from this to this I will take one rock mass, again the joint spacing is changing in this direction, then I can take that is a different rock mass unit, right? So in case of this joint, there are, in many cases, there are closed joints. In many cases, there are open joints, and this distance is known as pressure, and that may be filled with your I will say infilling materials. Okay, and you should know if this is a closed joint, it's okay, good. It gives you more friction. If it is open joints, then you will not get any cohesion. Okay, if it is filled, and suppose if it is filled with silica sand, then it may not hamper your stability. But suppose it is filled with calcite, then when it will be interacted with water, then what will happen? This will wash away, and there will be sliding, right? Again, you can see the joint surfaces. The joint surfaces are rough, right? This linear structure, these are known as lichen side, right? So we need to know in which direction shearing will happen. Okay, if shearing is happen in this direction, suppose this direction is A, then it can easily shear. But if shearing, this displacement is happening in this direction, then it shows some resistance. Okay, so this is a picture of Stuttgart. These are very small slope, 10 maximum 10 meter, and you can see that these slopes at the base you have fresh rock. Here you have boulder mix with laterite, and you have above this you have laterite. So you should categorize. Okay, I should categorize this zone 1, this is zone 2, and zone 3, right? And accordingly I should evaluate, because okay, I can get the rock mass classification for this one, rock mass setting for this one, I may get for this one, and this is the entire soil. So different zones should be studied. Suppose you are doing any stabilization measures, right? Why this discontinuity is important? You can say, okay, here we are saying that okay, the discontinuity is dipping like this, right? And if I know, okay, if I will do benching, the stability will be more. But what happens if I will do benching like this, like the case in B, right? Then this mass, they may fail. If I will do benching like this, parallel to my discontinuity like this, then there will be no free surface, so that this mass will move. Because if I am doing benching, I am removing this material, then what this is getting free space so that this body can move, right? So that these are very small things, but that should be observed in the field, and that should be properly noted. So while doing your geological investigation for any landslides, you first go for regional scale landslide investigation, then go for local scale investigations, right? So in regional scale, we do your deck study, right? And we get the literature. You see what is the regional. Suppose I will say I am going from Rishikesh to also Srinagar, that is Garhwal syncline. So I know this is a syncline that I will get faults, I will get fold, right? So that material units you need to know, and what is the structure, what is the bedding and joints we are expecting. Sometimes what happens? Suppose you have a slope that is covered with vegetation, but besides this slope that was exposed, then you can see, okay, if joints are present here and which is regional joints, okay, then we can expect that this joint also is present on that vegetative slopes, right? Okay, so that this gives you many ideas about the structure, what is the climate, what is the groundwater, right, and how seismic activity is there, right? From this, then we go for the local scale investigation. You take the locations of that landslide, then you put what is the type of landslides, okay, whether it is rotational, translational, what is the material involved, debris or soil, or it's a rock, right? So we can, okay, we'll say, okay, this is location is this. You take photograph, put the type of slide. Then you measure, okay, slide, what is the height, what is the slope angle, you measure all those things, right? Then you have you measure the ground cracks, okay, then you take what is the soil and rock types, and you can do the geotechnical analysis of this soil and rock types. Similarly, we see other associated feature on this landslide sites, right? I have to rush, that's why I want to show some. Yeah, so you can see here that you can do your once you know, okay, there are joints, you can do your kinematic analysis. From this kinematic analysis, you can say, okay, which type of failure is this one, right? Suppose if you can plot it and you see, okay, here there will be planar failure. If you have two joints are intersecting with each other, then you have a wedge shape block, and that will fail like this. And if you have joints were dipping opposite at very high angle, that may lead to toppling type failure, right? This is I have shown you. This is you can see here how there is a wedge failure because this they're intersecting with each other, and there is failure. This is near Coriola. What happens? You can see a rock block that failed from this part. If you analyze this, there are this joint and this joint, they intersected, and this rock fall on this, and you can see how much damage it has caused, right? If any traffic is nearby, then what would have happened? Then you can see if you have a debris site, we move to the slope. You can see, is there any tension crack? Is there any fractures there? If there is any tension crack, then water will ingress. Once water will ingress, then we know that the pore pressure will be more, and it will hamper your stability, right? So you can see here, even the material is removed from this toe portion, right? So if you are removing any material from the toe portion, that will also destabilize this mass, and that will going to fail, right? You can see this here. This is a progressive process, and you can see there are many cracks. So this landmass will fail, then this will fail. Okay, I will show you a nice picture of this of this one in later slide. This is you can see while we are doing any road widening activities, we should know where we should dumping our materials, right? If we are dumping at this, are we arresting the flow of water? Are we arresting any seepage? If you are arresting anything, if you are putting our dumping zone here and you are arresting this seepage from the slope, then inside the slope the water will be more, and that will give you more. You can see here the maintenance is also very important. Are you giving this adequate maintenance for this stability? You can see how this Gabbian wall is deformed. You can see here there is seepage of water, continuous flow of water, and it is stagnant here. So this all leads to instability. This will hamper your slope stability, right? At the toe portion where all this water is coming and it is here. So drainage of this water is important. Okay. So this is a very famous landslide that happened in Mandi. Professor Uday knew this, right? He had done work here. So you can see this is a very huge landslide, right? And I have gone to this crown portion in top of this landslide, and I observed that there is a very big circular fractures, ground fractures is there, ground crack is there, right? That means this is around this fracture is around at this level, which is around 30-40 meters beyond this main scrap, right? So what will happen if, as we know that if there will be rainfall and water will ingress and the metal property changes, then it may give you another slide. Okay, and this signature you are seeing, that you can see this Kotrapilli landslide here. You can see that in 2017, just before the landslide, there are some cracks, and this is after this landslide. So you can use your remote sensing, Google image to identify this, whether this landslide is progressing or not, right? And we have observed that there is a fault here in the Kotrapilli landslide, which is like this. This is the fault, Okay, that may be that is very near to this MBT, so that may be contributing towards this instability. So these are very few field observation I have shown you that we can identify the rock mineral, and we can take it up to do a better DPR. That will be very much helpful for your landslide study. And go for any detailing. Okay, go for the detailing of your work. Whatever color variation, either any grain size variation, whatever you are observing, you should put that. Right. So thank you for your kind attention. Thank you.
Thank you very much again, Dr. Pradhan. I think again, this is the one major point which should have been an emphasis in most of the landslide studies. Again, because mostly things are either only towards geotechnical or only towards geological when we talk about the landslide related aspects. I think it's this particular combination, as you rightly said, that there should be a very good communication between the geologist and the geotechnical engineer. If at all you want to really get into that risk reduction aspect of landslide. While studying or publishing papers, I think still things can go individually, but to bring it down to the practice, I think this is definitely important. And thank you very much again for highlighting this point, as well as a good understanding on the site-specific studies on geological aspect. So on behalf of all the participants, I thank you for giving us a very good lecture from your side. So
thank you very much.
So there are not many questions. Let me just check out. Just let me check out. There are a few points that you will have appreciated your and Mr. Ashish's presentation a lot. Not many questions. As I can see that there are more general questions. So we will take up if I find any important questions.
Okay.
So I will probably write to you in an email or get in touch with you. Okay.
Sure.
So
again, sure.
So thank you very much. So this should be the end of the day 2 for the webinar series, and tomorrow we have 2 presentations. One from industry, where from Macquarie Solutions, who should be again giving us an idea about the site investigation and also the mitigation aspects. And the second will be something interesting from faculty from computer science, who will be telling us some details about the landslide monitoring system, which is developed at IIT Mandi. So typically in line with whatever we heard in the on the first day by Dr. Nilima, we will be bringing out the behind the screen aspects of monitoring sensors, how they are developed, and how probably the developing techniques such as machine learning or artificial intelligence can be of use to predict these landslides much in time. So I'm looking forward again to meet all of you tomorrow for the third day and the last day of the webinar series. And we again thank all the experts for today's sessions. Thank you again.
Thank you all.
Okay, thank you.
And thanks, Professor Uday, for arranging this this session. Right.
Yeah.
We know that this landslide science is very important. If you see the hilly terrain, almost 17% of our landmass is landslide affected. So yes, this is nice. Exactly. Thank you very much.
Again, thank you. Okay, then I am terminating the session from here. So I am looking forward to meet you all again tomorrow. Same time, 3 o'clock.